All right, today we're going to talk about intersections of lines and planes. If you're watching the video, you can pause the video and try this warm-up question. We've already done this together, taken some time to do this in class, so we're going to just take it up here. So you guys may have noticed that something was happening here that was kind of strange toward the end. But the first thing that we're always going to check is whether these lines are parallel or not. Okay. So I can see pretty clearly here that 1, 7, negative 3 is some scalar multiple of 2, 4, negative 6. So if I multiplied, if my k value was a half, then these are scalar multiples. So because they are scalar multiples, the lines are parallel. And then we just need to determine whether this is parallel and distinct, so two distinct lines, or whether this is parallel and coincident, or two of the same lines. I don't think that you should have to use elimination here, but if you use elimination, you'll kind of notice that something strange happens where both of your parameters get canceled out, and then I think you end up with, you could either end up with a true statement or an untrue statement. What did you end up with, Aiden? Okay, so let's just kind of see how that pans out when we talk about parallel and distinct or parallel and coincident. So if I decide that the lines are parallel, really all I want to check is if they share the same points. So either I could check that this point is on line number 1, or I could check the reverse. I could check that this point is on line number 2. So I think I'll just use the parametric equations from line number 1. And I'm going to plug in the x, y, and z from this position vector for our second line. And then I'll solve for the s's. So we're going to plug in the point negative 3, negative 23, 10. And then we're going to solve for the s's that make that true. And then I'll just do the other one down here. So I'm plugging in the point for the x, y, z that's on the second line, and I'm seeing if that point is on my second line or not. So either they share, if they're parallel and coincident, they share all points, or if they're parallel and distinct, they share no points. So as soon as I prove that they share one point, I've proven that they're parallel and coincident, if they are. Okay, so here, just by isolating for s, we're getting negative 4 for the first one. We're getting negative 28 divided by 7, so that also gives us negative 4. And this one is 10 minus 2 divided by 3. Okay, so I think we actually get 8 over negative 3 here. So you got a true statement when you used elimination? Usually we get like an untrue statement.
I got 2 equals 2.
Did I plug something in wrong? No, I think I'm good, right? I think I'm good. Okay, so this actually tells us here that our lines, because not all of these s's are the same, these actually tell us that our lines are parallel and distinct. What does this mean as far as points of intersection? If they're two parallel, distinct lines, they're their own lines. Okay, yeah.
So if I have a true statement, does that mean they're parallel and distinct?
So usually that's supposed to mean that they're parallel and coincident, but I'll have to take a look at your thing there. You'll see a little bit more today about like true and untrue statements. Okay. So that's kind of a summary of what we did yesterday. We also actually solved for some points of intersection, so there were some longer versions of these questions where we actually have to use elimination. But we're actually going to use the same kind of process in our lesson today to solve for intersections of lines and planes. So let's just do a quick discussion here. What are the different possibilities that we could have for a line in 3D space intersecting with a plane or a flat, or not necessarily a flat surface, but a surface? How could this happen?
You mean like this and then this?
Yeah, okay, so one of the obvious ones is the line cuts through the plane, right? So it goes through the plane, you have one point of intersection. What else can happen?
Line on the plane.
Okay, so if the line is on the plane, how many points of intersection would we have? Infinite. And then are there any other scenarios that we could have in 3D space?
Line's parallel and distinct.
Okay, so if the line's like floating above our plane up here, then I have no points of intersection. So that's perfect. So those are really the only three options that we can have. We can have 0 intersections where they're parallel and distinct. 1 intersection where it's not parallel, so it just cuts through our plane. And infinite intersections, which means the line is literally on the plane, and we call it coincident or coincidental. Okay, so let's just say these are our 3 planes in space, and then we have our lines. So I can either have a line that is parallel and distinct, so that means our line is like kind of floating above our plane and it's not going to touch our plane. I can have our 1 intersection. Maybe I'll draw this one. So my line literally like cuts right through my plane. Okay, or I can have a line that's right on my plane, which means that it's like inside, oops, sorry. It's inside the plane, and then I'm going to have infinite points of intersection there. So those are kind of the 3 visuals of what we can have. All right, so we're going to determine if our line, we're given the symmetric or the parametric equations for our line, and our plane intersect or not, and if so, we're going to find that point of intersection. Now, the only time that I could find a point of intersection is if they're not parallel. So if my line and plane happen to be parallel, then automatically I know that they either have 0 solutions or infinite solutions. So the quickest way that we can kind of, or I guess the way that makes the most sense here, is if I have an x, y, and a z, and I have an x, y, and a z here, I can actually plug the parametric equations into the equation for my plane. Okay, so I'm going to take 5 plus 2t and plug it in for my x. And then I'll take the parametric equation for the y and plug it in. And for the z. Okay, so now we have 1 equation, and there's 1 unknown in that equation. Can we solve for the unknown? I think we can. So we're just going to do a little bit of distribution here. Expand and simplify. What's that, 65? Okay, and then when we kind of gather things all together, I'm also going to move this 29. Actually, I don't think we necessarily need to do that. We'll move all the constants over to the left side here, or the right side, sorry. And we'll leave all the variables on the left side. So when I gather my variables, I'm getting negative 53t. And when I move these guys all over and I simplify, I'm getting positive 53. Okay, so there's a couple things that will happen at this point. Either I can solve for t and I get a value that makes sense, which in this case, if I just divide out the negative 53, I get t equals negative 1. Is that acceptable? Does that make sense? If I have like a value? Yeah, it makes sense, right? So this is actually telling me that because I get a solution that makes sense, this is actually telling me that a point of intersection exists. So if my t is negative 1 and I get something that makes sense, we have one intersection point. Yep.
So like if it wasn't on the line, we'd get like an impossible number.
Yeah, so I'll kind of show you in a couple other examples some different things that you might approach. So therefore, we have one point of intersection. And any ideas as to, now that we have t, how we can find that point of intersection? Yeah, so we'll just plug it in to L1, and we'll have our point. Okay, so here we're getting 3, 0, and negative 1. Okay, how can I double check that this is the correct point of intersection? Yeah, so if we plug in our point of intersection into the equation for the plane, I should get a true statement. I should get 29 equals 29 in for the x, y, and z once I simplify on the left side here. Okay, so you can do a quick little check. If you've plugged in your t value into your parametric equations for your line, that point of intersection should be both on that line and on the plane. Questions for this one? Not too bad, right? Pretty straightforward. We're just going to plug in the x, y, and z, solve, and then plug in our t value. Can I flip? We're all good? Okay. So similarly, I just want to show you like another thing that you might approach here. So we have plane number 2 and line number 2. I'm going to do the same thing. So we're going to plug the parametric equations into our plane. Okay, if you happen to be given something like the equation of the line in vector form, you can always create the parametric equations from that. And then we're just going to expand and simplify here.
Sorry.
Did I do something wrong?
No.
I'm okay? Okay. Okay, so I think we can kind of see here our t's are kind of canceling each other out here. So we have 0t, and then if I'm bringing this over to my other side and gathering in all of my constants together on that right side there, I actually get the value negative 31 when I bring that all over. Okay, so this is what I mean between like a statement that makes sense and a statement that doesn't make sense. I can't have, so I did put 0t on purpose just so we can kind of see whether this statement does make sense. Technically it's 0 equals negative 31, but if we have 0 t's left, right? So 0 times something, is that ever going to give me negative 31? No, it's not. So this is not possible. So that is telling me right there that I have 0 points of intersection. I actually don't even have to go further with this because this statement is not solvable, right? This is not possible.
I got 31. 0t equals 31.
Oh, is it?
Because it's negative.
Oh, yeah, true. Sorry, this is positive. Same thing though.
Yeah.
So this is not possible. As soon as you get a statement that doesn't make sense like this, we know that they are parallel and they are distinct. Okay, so untrue statement tells us that we have distinct lines, and we have no points of intersection. I actually don't have to go further than that. Does that make sense? Questions on this one? Okay. All right, and then I want to show you kind of like a third version of what you might approach if they're parallel and coincident. So here I'm actually just going to create my parametric equations quickly because they're not given. It's okay. Okay, so just separating our line out into its parametric equations. Okay, and then as usual, we're going to plug them into our equation. So same process. So expand, simplify. Okay, you don't have to keep the t in there if you don't want to. That's totally fine. So you'll notice here that our t's are actually canceling out. That's equal to 0. And then when I gather my constants, even if I don't bring them to the other side, if I just gather them together, I have negative 12 plus 11 here, and I have negative 1 equals negative 1. Or if you moved your constants over, you would have 0 equals 0. So same kind of idea. So because we're left with a true statement here, this should tell us that we have infinite points of intersection. So the line is actually in the plane itself. And I don't need to go any further because everything is a point of intersection between that line and plane. So therefore, if we get a true statement, we have infinite points of intersection. Okay, so really guys, there's 3 options for how a line and a plane can intersect. And there's 3 options for what I'll get when I'm solving for that point of intersection between a line and a plane. Either I get a statement that makes sense and I just solve for the parameter, which means I have a point of intersection. I get a statement that doesn't make sense, which means they're parallel and distinct, no points of intersection. Or I get a statement that is always true. If it's always true, that tells me infinite, right? So it means it's true, but literally always. So infinite points of intersection. I can't solve for one specific point just because every point on this line is inside the plane. I mean, I could solve for a specific point just by plugging in any parameter for t, but it's literally every point on the line. Okay, so if you want to just jump back here, you can actually just write yourself a little summary here. So if you have 0 intersections, you will get an untrue statement when you try to solve. Something, for instance, like we got 0 equals 31, that doesn't make sense, right? If we have 1 intersection, we will be able to solve for the parameter as usual. Okay, so it will seem like everything is working out as usual and totally fine. Here you would get a always true statement. So for example, you could get something like 0 equals 0 or 10 equals 10 or whatever. Okay? So you can't really solve for the parameter, but you get something that makes sense, right? 0 equals 0, 10 equals 10. So that's kind of the summary. You can only really get one of those three things. Okay? There is a way, without actually solving, that we could check if a line and a plane intersect. So I just want to show you guys that little check that you can do. So here we have a line, a vector equation of a line, and a scalar equation of a plane, or sometimes called Cartesian equation of a plane. Can somebody tell me what the normal of this plane is? What's the normal of the plane? Close.
4, 2, 0. 4, 0, negative 2.
4, 0, negative 2 is correct. The y is 0, right? Okay, so the normal of this plane, can somebody explain to us what I mean when I say normal? What does that mean?
Perpendicular to the point? The line.
To the plane.
Plane.
Okay, so if I have my plane, just so we can have a little visual, if I have my plane, that was a bad plane, but you get the idea. If I have my plane, my normal vector is the vector that is perpendicular to this plane, right? So that's my normal vector. If I want to know whether this plane is parallel to my line, I can use the direction vector for my line. What do I know about the normal of the plane and the direction vector of the line if the line is parallel to the plane?
The dot product will be 0.
That's correct. Okay, so if I have a line that's either kind of like floating above my plane or a line that's inside my plane, those lines, if they're parallel with my plane, they are perpendicular to the normal. So my lines, if I dot them, if I dot the direction vector of my line with my normal vector from the scalar equation of the plane, I should get 0 if my line is parallel or not. That will basically just tell me whether I have one potential point of intersection or whether it's a parallel line. So if L4 is parallel to the plane, the normal, and maybe we can call this M for direction vector, dotted with M will equal 0. Okay? So we're just going to check the dot product of those two vectors, 4, 0, negative 2, and negative 2, 1, negative 4. Okay? So 4, negative 2. What's that, Mark? No. If the line is parallel to the plane, then it will be perpendicular to the plane's normal. Right? Which means that the line is parallel to the plane, right?
Yes.
Okay, so this is the check that we're going to do. So we don't know for sure whether this is 0, but we're checking whether it's equal to 0. So I get negative 8 plus 0 plus 8 equals 0. And we get a dot product of 0. So this tells me that our plane and our line are what? Okay. So with this, we can say that the line and the plane are parallel. If I wanted to check whether the lines are now parallel and distinct or parallel and coincident, does anybody have a way that we could do this really quick? How could I check if that line is in that plane or if it's not in that plane? Mark? Okay, so if we take this guy and we plug it in here, either they share all points together, right, or they share no points. So either I will get a true statement or an untrue statement. So if I want to check whether they're parallel and coincident or parallel and distinct, I will plug in a point on that line into my plane and see if that point is on the plane. Okay, so we'll have 4 times 1. Y is already 0, and then z times 1. And the question is this a true statement? Well, I think we get 2 equals 11 here, which we know is not true. So what does that tell me? Do they share points or do they not share any points? They don't share any points. So they're parallel and distinct. Okay, that's kind of a weird sentence. We'll probably just say L4 and pi 4 are parallel and distinct, but whatever. Okay, so again, we're looking at that, do we get a true statement, do we get an untrue statement kind of idea. Okay, so that's a really quick check that we can do to see whether we have an actual point of intersection or not, or like infinite points of intersection or whatever. Any questions? Okay, if they were parallel and coincident, we'd get 11 equals 11 here. So that tells us the point is on the plane.